Okay, to start this video, I'm actually got some questions I want you to try this to start. Note, these are not the exact same questions you may be getting on your clicker quiz. These are just things to try to review from yesterday, because I think it's good to continue to review as we go. So for each of these, I'm going to give a short break where I want you to work on it, and then I'll show you how I solved it. So stop this here now and try this question. This is from last class's material. Okay, hopefully you've done that. So this problem it's asking is which shows a decrease, there we go. It started flipping. There we go. Sorry about that. My little pen has a button on the bottom, which I've not gotten used to still. It clicks the thing for me, and it's trying to be helpful, but it really just gets in the way. So what we need to think about is what causes changes to entropies. So first we have phase changes. Our phase changes go from the order of our solids have the least entropy, our liquids have the next, and our gases have the most entropy. So for example, if you go from liquid to gas, you're increasing entropy. So A is not a good answer. B, C, and D, they stay the gas phase. And B has a different type of phase change. It's not solid liquid to gas. So this will bring us to our next thing that changes entropy. We should remember that with changing entropy, if we are dissolving, so going from solid to aqueous, that is an increase. So in this case, it went from solid to aqueous, so that's increasing entropy. It makes it a poor answer. If it had started at aqueous on the left side and moved to solid on the right side, then that would have been a decrease in entropy. So you can have something like that, but that means you're going from dissolved into solid. Now, we also talked about the idea of complexity. I'm trying to write on my paper rather than the thing. That would be helpful. So our number of molecules was something we were worried about. Molecules. So increased molecules equals more entropy. So here on C we have 2 and 2, so that's not helpful for that one. That won't tell us anything. But on D we go from 2 molecules to 1 molecule. Since we're decreasing the number of molecules, that means we decrease the entropy. That makes D a good answer. It would be a decrease. Now, one we didn't talk about here, because it wouldn't really work with the chemical reaction so much, is we also learned during our study that increasing molar mass leads to increased entropy, which doesn't come up with any of these because they have the same number of atoms on the left and right side. We also learned that as temperature goes up, we tend to have increasing entropy, and neither of those were listed there, but those are other types of things we could have. We could have where we had different descriptions of what occurred, and one of them was we raised the temperature of this thing, which is a way of saying that's an increase in entropy. So now, here's a second example where this one we actually want to calculate delta S and the change in entropy. So I'd like you to pause this here and give it a try. Okay, so let's look at how this would work. So our delta S is equal to our products minus our reactants. So we've got to calculate both of them. So for here, our products, first we have 2 waters. So that would be 2. And then water has an energy, if we look it up, it's right there. It's 188.8 joules per mole Kelvin. Note, it matters what phase it is. This is gas. This is gas. If you had a larger table like you might on your test, if you looked at the liquid value, you would get the wrong answer. This came up on one of the clicker questions, I think, that we did last class. So now we got to subtract the reactants. So I'm going to put this in brackets because I'm going to add all the reactants together and then subtract the whole thing. So for our reactants, we first have 2 hydrogen gases. So that's this one. So we'll have 2 times 130.7, and you're going to pretend like I wrote a joule per mole Kelvin there because it won't fit. And then I'm going to add to that my 1 oxygen. So it only has 1. So it's 1 times 205.2 joules per mole Kelvin. So then if I total everything up, my products is going to give me a total of 377.6 joules per mole Kelvin. Whereas my reactants, when I subtract them, I'm going to be subtracting 466.6 joules per mole Kelvin. So you combine all these together, and we get that our delta S equals negative 89 joules per mole Kelvin. And that will be answer A. I want to note something about when you see entropies and enthalpies and free energies. You're going to notice that sometimes they get listed as joules per Kelvin and sometimes joules per mole Kelvin. This is usually because it's how you're looking them up when you look at them next to an equation specifically. So when I have an equation like A plus B goes to C, it's going to list delta S in just joules per Kelvin. The reason it does this is because it assumes because it's next to this chemical equation that we're accounting for the fact that we're talking about moles with this case. So like 2 moles of hydrogen plus 1 mole of oxygen produces 2 moles of water, gas, and that has an entropy change associated with of negative 89 joules per Kelvin, assuming you have 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water. That's why they do that. And I don't like that it's inconsistent, but I did write the answers in both the ways they'll be written. So if you would look this up in a table, you would indeed see this joules per mole Kelvin here. However, you're going to see in like the problems in the textbook, you would see this written next to the equation here in joules per Kelvin. I realize that's frustrating because I don't like that they're inconsistent, but it's how our field does it. So I'm trying to match up with how our field would do it so that we are consistently inconsistent with how they write it. They do mean it. And so to be fair, it's not actually inconsistent. It's just there's some assumed knowledge in it, which when you're first learning it, there's no reason to pick up on. It's like, wait, why did they do it here and not there? So that's the reason. You see it next to an equation, you will usually see it as just joules per Kelvin. Note, if you look at enough books, eventually you'll see one that says joules per mole Kelvin as well. They both are intended to mean the same things, so they're not wrong in that case. So just as a heads up, because I know that can be frustrating, and if I don't say something, you can't ask me, especially because you're not in class right now. So let's try one more. So I want you to pause here and take this problem and try to calculate this. And if you're unsure of what to do, remember, think about delta G and how it relates to things being spontaneous. Okay, so what we need to do is we need to calculate what our delta G is, because you need to know that to be able to figure out some information. Well, not exactly delta G. What you need to calculate, is when delta G equals 0. As a reminder from last class, delta G0 is your bright line. So this is our separator of low and high temperature. So in this problem, you'll notice that delta H is a positive and delta S is a positive. Okay, I'm going to sneeze, so I'm going to mute and I'm going to stop for just a second. Okay, hopefully I don't sneeze again. So we have delta H and delta S are both positive. In that case, that means that we're going to have high temperatures being spontaneous. Note, this problem already tells you at temperatures greater than, which is a way of going ahead and telling you that it's high temperatures, but the problem wouldn't have to tell you that. You could have answers where you have both greater than and less than signs as options. So you have to look at the signs of enthalpy and entropy to figure out whether it's the high or the low temperatures that are spontaneous. So since we now know that high temperatures are spontaneous, we need to know where is the bright line, where is the separator for this reaction? What counts as high, what counts as low? And that we find by finding delta G equals 0. So I have 0 equals delta H is 131.3 kilojoules per mole. Minus T is what we're looking for, we don't know. And then we have delta S. I want to point out something because I know that units are something people don't write down a whole lot or pay that much attention to. Enthalpies are reported in kilojoules. Entropies are reported in joules per Kelvin. The temperature takes care of the Kelvin part, but the joules is not the same as the kilojoules, so you have to convert them both to be the same. So you can either convert delta H's into joules when you're combining them, or in my case, I'm going to convert entropies into kilojoules. So my delta S is going to be 0.1336 kilojoules per mole Kelvin. And I wrote that other thing too close. So now we have to move, I'm going to move this 131.3 over. So I'm going to get negative 131.3 kilojoules per mole equals negative T times 0.1336 kilojoules per mole Kelvin. So now I'm going to divide both sides by negative 0.1336, negative 0.1336 kilojoules per mole Kelvin. And what you'll notice is the kilojoules and the moles will cancel, and this whole thing cancels, and these two negatives cancel, and these two negatives become positives. So when I do all of those changes, I'm going to get 983 Kelvin equals T. So what's important is in this problem, you could just circle this and say it's 983, but for a problem that might be written a little differently, if you had both greater than and less than, it's important to remember that T is greater than 983 for spontaneity, and that's in Kelvin. There you go. So hopefully those help to review that material. And what we're going to do now is we're going to shift into some new material now. So we've already mentioned free energy at the start of this, but we need to do some more with that free energy. What are some other things we can calculate? So the free energy of formation is mostly what we're going to talk about, and that's how much the free energy changes when 1 mole of the compound forms from its constituent elements. That means, for example, if I wanted to know the free energy of, let's say, water gas, its free energy would be associated with when I combine hydrogen gas plus half an oxygen gas to make water. That's what the delta G we're looking up for is. As a reminder, in case you don't remember it from 1211, when we're working with these thermodynamic quantities inside of tables, we're always looking at how much it takes to make 1 mole exactly. For that reason, you will sometimes see fractional things on the left side. Even though you don't actually have half an oxygen in your reaction normally listed, we will here because our tables are for how much is it for 1 mole. So to make 1 mole of water, you only need half a mole of oxygen. So that's how we're going to list them. And as a note, the free energy of formation of pure elements in their standard states is 0. And that's because we have to set delta G at some value. It's not like entropy where it has an explicit value that can get there. It's always a relative thing here. We're looking at changes in free energy, not absolutes. So since we're looking at changes, we've set these as these are our starting points. And so you can look up for any element. The one where delta G equals 0 is going to be the one where it's in its pure state. So this is an example of one of the small tables. You can use these to then help figure out problems in 2 slides, not this slide. So how can I do this? So just like with entropy, if you're at 25 degrees, we just take all the products, subtract all the reactants, don't forget to multiply by the number of moles. As a side note, unlike entropy, some of your delta G's can be negative, just like you had with enthalpies in 1211, so pay attention to signs. Also note, at temperatures other than 25 degrees, assuming the change in delta H and delta S is negligible, we can just use the equation delta G equals delta H minus T delta S and look up delta H and delta S. Now, I will note that it is not always negligible. As we mentioned earlier on this review, is the entropy does change with temperature some. Having said that, I will never ask you to do this for a problem where it is not negligible. So you can treat it like it is if we ask you to do something like this. Just assume, oh, you want to know it at 30 degrees? Sure, I can plug all this in and that's fine at the answer. Technically, there is a little bit of error, but it is a good approximation for it. So that's how we're going to be doing it in this course. If we need to do this at other temperatures, and we don't have some data to use, like in terms of actual reaction, we have to look things up in tables, we will adjust it using this equation. Note, that does mean at higher temperatures, you have to actually look up the delta H's and delta S's. You can't just look up the delta G's and add and subtract them. You have to actually find delta H and delta S, put it in this equation, and multiply it times temperature to account for that. Because the delta G is always going to change significantly. Delta H and delta S sometimes won't change significantly, depending on how far away you're going. So let's do an example of how we would do this summing thing. So I want to know the change in delta G from the reaction below. 2 waters plus an oxygen goes to 2 water gas. So just like we did with entropy, the problem's going to look incredibly similar. We're going to do products minus reactants. And it's the sum of... I was trying to make a summation symbol. That was a really poorly drawn summation symbol, but you know what I was doing. There's a picture of it on the previous slide. So products, we just have 2 waters. So we have 2 times... One second, I'll have to redo all these calculations. I had done these ahead of time, so I wouldn't have to solve them while you were watching, but this sheet I put aside, so we're just going to do this live, like I would in class. So products, 2 waters. We have negative 228.6, and all of these are going to be in kilojoules per mole, so I'm only not going to write it so I have enough room to put it in here. Please write it when you're keeping track of things, since there's so many problems that switch between joules and kilojoules when you're doing stuff. Now we're going to have to subtract the reactants. So we've got 2 hydrogens, those are at 0. And we have 1 oxygen, those are at 0. So this one, 0 and 0. So we just have to do 2 times negative 228.6. Would help if I put a decimal in it. 228.6. And we're going to get that our delta G of formation is negative 457.2 kilojoules per mole. Or if you saw it written right next to this equation, we would just write delta G of formation is negative, I'm going to try not to accidentally flip the slide, 0.2 kilojoules, and we would stop with that. So note, for the purpose of your test, I promise I'm not going to try to trick you and ask you 1 in kilojoules and kilojoules per mole. It'll just be one of those, and you can account for that. So there is no way in my assessment ability to try to trick you with this. So I promise that won't happen. Just note when you look at different formats or when you look up different review videos, it may look a little different. So that's how you make this calculation with that. Let's talk about some other things we can do with this. So what you can do with delta G is you can express it instead as a series of reactions, where the sum of the delta G values of those individual reactions is the delta G of the total reaction. So initially it sounds like, okay, you just said a bunch of words that don't mean much. I'm hoping you remember your 1211 Hess's law. It's the same idea. So what we're meaning is, let's say I have a reaction, A goes to C. But I also know A going to B and B going to C happen as well. Now let's say these are easy to measure or in known tables. So like you already know these things. We've done a bunch of experiments. We know how hard it is to get A to go to B. We know how hard it is to go to B to go to C. On the other hand, this is unknown or hard to measure. So you can combine these two reactions together and it will give you the same value as if you just looked at the reaction A goes to C. So we're going to do this by making changes to these reactions like A goes to B and B goes to C to figure this out. And I promise I'll do some examples because what I said, if you don't remember Hess's law, is probably sounding kind of rough. So before I can actually go over it, I have to go, how will I make changes when I can't just easily add things together? So first, if we reverse a reaction, we change the sign of the delta G. What do I mean by this? If A goes to D, has a delta G equal to positive 24 kilojoules, then what's also true is if D goes to A, then delta G has a value of negative 24 kilojoules. We can also multiply them by factors to make changes to them. So taking that same idea, 2A goes to 2D will have a delta G value of 48 kilojoules. And that's supposed to be a D, not a B. D, trying to fix it, just making it worse. That's a D, I'm telling you out loud. There we go. So we can do these same types of relations we did in 1211 with Hess's law. So the reason why we're switching sides and multiplying by things is when we add them all together, we need to make some of the components disappear. And the easiest way to do this is to actually do an example. So let's try solving this. I want to know if I take C carbon diamond in the solid form and turn it into graphite, what is the delta G associated with this reaction? But let's say these are the two data points I actually know. So what I do is I can make changes to them. So when I add them together, everything cancels with the C diamond and this carbon graphite. So here you'll notice what we do is we look for things in these reactions that are different than what they are in the top reaction. What do I mean by this? First, let's look for carbon diamond. Well, it's already here and it's a reactant. They're both reactants. So the first equation is actually in a pretty good spot. It's where it should be. But if I go to graphite, oh no, graphite is a reactant here, but it's a product here. So we need to change something. So I'm going to reverse the bottom reaction. I'm going to say, what if we switch it into carbon dioxide gas, reacts to form carbon graphite plus oxygen gas? Well, then I need to change my delta G because now it's going to be positive 394. So since I've made that change, I now have my diamond graphite in the right, or diamond carbon in the right spot, and my diamond graphite, my graphite. Diamond, carbon, graphite, carbon are both in the correct spots now. So if I were to add these up like an equation, so we'll also have our carbon diamond, I'm going to abbreviate that, goes to plus oxygen gas, goes to CO2 gas, and that delta G naught didn't change because we didn't do anything to it. So if we combine these, what we can do is we can cancel things out that occur on opposite sides. So for example, here, CO2 is a reactant. Here it's a product. Therefore, if we were to combine them, they would cancel because there'd be one on the reactant side and one on the product side, which means it doesn't change at all. Similarly, our oxygen here cancels and our oxygen here cancels. And we're left with C diamond goes to carbon graphite. And when I combine those, I would get a delta G naught of negative 3 kilojoules. So this is our change in free energy. The reason we added everything up at the end is it needs to match this original equation. If it doesn't match, you need to make some more conversions or make some more changes so that you're able to get just that reaction with no extra things left over. So let's take a look at another example. So for this one, make sure, I want you to, and I know this problem is harder than the one we just did. I'm hoping you can remember some from your 1211 Hess's law. I want you to give this one a try. Try to figure out how to make it so you have N2O plus NO2 goes to 3NO. As a reminder from Hess's law, try to pick ones that only occur in one reaction. By ones, I mean reactants or products. So for example, N2O only shows up in equation 3. So that's a good place to start with. Try changing equation 3 so it matches the top reaction. And leave things that occur in multiple places. Like in this case, your nitrogen monoxide, the NO, it's in equation 1 and 2. So do it at the end. Okay, I want you to give this a try now and see if you can figure it out. Okay, having said that, I'm going to work through it now. And we'll see how it goes. So, like I suggested, we're going to start with this equation here. And you'll notice there's two N2Os here, but I only want one of them. So I'm going to multiply this by a half to help make it easier. So when I do that, and it's already on the reactant side, so I don't need to change the sides. So we'll have N2O gas reacts to form N2 gas plus half an oxygen. When we do that, we also have to half the delta G. It's still negative because we didn't change sides, but I have 207.4, and I'm multiplying by a half or dividing by 2, both the same thing, and I get 103.7 kilojoules. Now, I said I'm going to leave the NO till the end. Let's look at the NO2 next. It only occurs in the top reaction here. And this one, you'll notice, it's on the product side. So we're going to need to multiply by a negative number when we flip it over. There's also two of these and I only want one. So we're again going to do the 1/2 thing. So this is going to give me, I flip the sides, and I get NO2 gas reacts to form NO gas plus half an oxygen gas. And it has a delta G naught of, we do a negative times a negative, so it's now a positive. And then we have 71.2 times 1/2. And I'm going to get positive 35.6 kilojoules. Now the last one we're left is the NO. So you'll notice you have one NO in this equation here. You also have 2 right here. 2 plus 1 will give you 3, and they're both on the product sides. They're already on the right side, so I don't need to change equation 2 at all. So I have N2 gas plus O2 gas forms 2 nitrogen monoxide gas. And that, the delta G naught stays the same for that. So what I have to do now is I have to check when I add these together, do I get the top reaction? If not, I've made an error somewhere and I need to make some additional changes. So first I'm going to start with, I'm going to do all the reactants first. So we have one N2O written here, none anywhere else, so they don't cancel. We have one NO2 here. It doesn't show up anywhere else, nothing cancels. I have one nitrogen on the reactant side and one on the product side. Those both cancel. I have one O2 on the reactant side here. I have half an oxygen and half an oxygen. Those add up to 1 as well. Since we have 1 on both sides, they're able to cancel. Note, if you had 2 on one side and 1 on the other, then only 1 would cancel and you'd be left with 1 left over. So that can happen sometimes too. Now, let's check the remaining products. NO and 2NO. Those don't cancel because there's nothing to cancel with. They're on the same side, so we're going to add those together. So if I add up everything that wasn't canceled, I get N2O gas plus NO2 gas reacts to form 2NO gas. And since that's the reaction, and that is what we wanted, we can add up those delta G values and they will give us what we want. And that'll give us a delta G naught of 107.1 kilojoules. I want to note something about this problem I just did. I know that if you weren't comfortable with Hess's law, or maybe your class didn't get to it, what I did might have just looked like black magic. I do think this, of almost everything we teach, is the thing that increases the most in ease of doing with lots of practice. I want to strongly encourage you, even if you're not practicing a lot of other things because you're very busy, try to do some more of these problems. We have some in the text you can use. I know I have at least a couple on your review guide. If you look up YouTube videos if you don't like me. You can look at someone else. Looking up Hess's law will give you lots of problems like this. Or if you literally just Google Hess's law examples, free energy, you can find examples where people do this. Practicing these helps a lot, I think, because they're the type of problem that when you're trying to do them at first, they seem impossible. And once you see how to do them, they're some of the easiest problems we can do. So I think practice here is tremendously important. We'll also make sure to do some at the front of my lecture on Tuesday. We will keep practicing these. I know that if you haven't seen Hess's law before, this is somewhat difficult because it is written assuming you saw that in 1211, because it's otherwise the same. So we can only practice it so much since it's something that is done identically to how you did it with enthalpy in 1211. And if you had a little trouble there, hopefully the experience there with a little bit more work here can get you through it. Having said that, we need to do a tiny bit more with free energy before we're done for today. So I'm going to talk about free energy under non-standard conditions. What does that mean? We need to define standard. So standard is normal state at the temperature we decide. So at any particular temperature, usually it'll be 25 degrees Celsius, but a problem can tell you something different is standard for it. But whatever temperature you're at, it should be in the appropriate phase. For example, water at 25 degrees is a liquid. It is not an ice cube. So if you had a problem that was working with water as a solid, that's not its standard state at room temperature. The partial pressure of any gases in your problem should be 1 atmosphere. Your concentration of any solution should be 1 molar. I want to point out, this doesn't mean you can't work with things that aren't 1 atmosphere, 1 molar. It's just that you don't use delta G naught then if you're working with those. What you can do then to convert between delta G naught and delta G is we're going to use that idea of, sorry. There we go. So we're going to work with that idea you learned in equilibrium called Q, the reaction quotient. So we have this reaction, delta G equals delta G naught plus RT ln Q, with a note that this R is 8.314 joules per mole Kelvin. But since delta G is usually kilojoules per mole, you will want to use 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. That's a 3, not a whatever else it was. Or you could convert delta G to joules. That's fine too. Just make sure you account for that. You can't ignore the units. You'll notice in this chapter they definitely come up a bit, the difference between joules and kilojoules, and you have to pay attention to that. As a final note, at equilibrium, delta G equals 0. So we said this earlier when we were talking about whether things are spontaneous or not. So what that can tell us now is we have this reaction here. Delta G naught equals negative RT ln K. So if you know the free energy, you can find the equilibrium constant. If you know the equilibrium constant, you can find the standard state free energy. This is helpful to us, and this is how these two chapters end up connecting. You're able to use one of these quantities to find the other, and we'll work an example in, I believe it's 2 slides. We have to first do the non-standard condition slide first. So let's take this. We want to know, we've got this reaction, 2NO gas plus O2 gas goes to 2NO2. It has a delta G with it. As a side note, is that spontaneous or not normally at standard conditions? You should note that because it's negative 71.2 kilojoules, it's a negative value. That means this is spontaneous. I want that to get really automatic to you. Anytime you see a negative delta G, that means spontaneous. Anytime you see a positive, that means non-spontaneous. So what we want to know instead is what if you weren't at standard state? Because a lot of times we're not. What if you had a smaller amount of NO and oxygen, but you had more NO2? Let's figure out what that delta G value would be. So to do that, we need to start by finding what our reaction coefficient is. So remember, you calculate it just like an equilibrium coefficient. The only difference is conceptual in that we're saying this might not be at equilibrium. So we need to look at the specific values at this moment. So you remember it's products over reactants. So for our products, we have NO2. So since these are all gases with pressures, we do the pressure of NO2 squared. Divided by our reactants, we have the pressure of nitrogen monoxide. There's 2 of them, so it's squared times the pressure of oxygen gas, which doesn't get squared because there's only 1. We plug these values in, we get 2 squared divided by 0.1 squared times 0.1, which gives us 4 over 0.1 to the 3 is 0.001, which if we do that will give us a Q of 4,000. Note, we don't know K yet, so that doesn't tell you anything yet. It's going to be used in our equation. So now we got to plug everything into this equation here. So what we want to know is, what is the delta G? That's the thing we don't know. We do know what the standard state value is, though. It's negative 71.2 kilojoules per mole. Again, like I talked about last time, you'll see per mole, sometimes you won't. When it's written next to the reaction, you won't see per mole. Everywhere else we'll put per mole with it, just to remind you. Otherwise, it may look weird, like, wait, why does my unit not work out? R has moles in it. How did that get accounted for? It did by that step there. So we have plus our R, 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, times our temperature. We know our temperature is 298 Kelvin. And we know we want to take the natural log of our Q, which is 4,000. So now we have delta G equals, if we combine all of these together, we will get negative 50.7 kilojoules per mole. As a reminder, this natural log 4,000 is just a number. You can put it in your calculator. I'll do it right now. If I pick the ln of 4,000, I get 8.294. And I multiply it by those other numbers, and that will give me my units. Also, to point out, these kelvins canceled, so that's why I'm left with kilojoules per mole. Natural logs don't have units, so we get our delta G here. Now you'll notice this actually isn't finishing the question yet. The question asks, is it more or less spontaneous? So it is still spontaneous because it is negative, but it is less negative than negative 71.2. Therefore, we are now less spontaneous. So it would still happen, but not as much. It doesn't have to change as much as it would if it were at standard state, which would be 1, 1, and 1. So that looks at how we can use that equation to figure that out. You could also have subproblems where they just ask, is it spontaneous or not, period. That's probably more common. So you might have a problem where when you change the conditions, it becomes positive instead. Well, then it would be non-spontaneous. Or if you get exactly 0, then it's at equilibrium. It's already there. Please note that if I ask you about whether something's at equilibrium or not, you might get something like 0.0001 kilojoules per mole. Something like that, I'm fine with you saying is equilibrium. I'm going to make sure that when I ask you these questions, I don't ask ones that are super borderline. Like, is this spontaneous? Negative 0.00001. Wait, is it that or not? That's not fair. So I will make sure its answers like negative 5 or negative 10 or negative 360, something like that, so that it is reasonable for you to be able to identify that. And it's not a guess on your part, especially because they're multiple choice. You can't write out an explanation to me of, oh, I think this is really close. I'm not sure what you want. I know you can't do that on these tests. So now we want to use this to figure out, I want to talk about this equation with our equilibrium part. So we want to figure out some more about equilibrium. So we know delta G of reaction equals 0 at equilibrium. So if we take our equation, delta G equals delta G naught, and make sure it's a minus. It was indeed it's a plus. This is why we check things. ln Q. But we're at equilibrium. Remember, at equilibrium, Q is the same as K. So that's why I'm able to put this K here. This is only because we're talking at equilibrium. It wouldn't be normally. So we said at equilibrium, delta G equals 0. Let's plug that in there. We get 0 equals delta G naught plus RT ln K. Well, now I'm going to move the RT ln K to the other side. We get negative RT ln K equals delta G naught. So this means we can use delta G naught to figure out K, K to figure out delta G naught. You should, this exam is open note. If you're taking this in 2020 during our pandemic, this is open note. I say that in case someone sees this video later. But assuming you're doing that, make sure you know where this equation is. You're going to use it some. And remember that when we talk about equilibrium and delta G together, this is the equation you can use to connect them. So if K is less than 1, delta G naught will be positive. And that means the reaction is spontaneous in the reverse direction under standard conditions. What do we mean by that? If you have A is in equilibrium with B, and K is less than 1, if K is less than 1, delta G will always be positive. And if delta G is positive, that means it is non-spontaneous as written. If it's non-spontaneous as written, that means going backwards, it is spontaneous. So the reaction will spontaneously go more towards A and less towards B. On the other hand, if K is greater than 1, delta G is always negative. And in both these cases, I do mean the word always because of how the equation works out. You can solve it with any number. Anytime k is less than 1, delta g is always positive. Anytime k is greater than 1, delta g is always negative. So if delta g is negative, it is spontaneous in the other direction, in the forward direction. So it goes more towards B than A, which matches what we know about K. Remember, when K is greater than 1, that means products are favored over reactants. But in standard conditions, the answers are going to be 1 molar or 1 atmosphere, depending on if you're talking about aqueous or solutions or pressures of gases. So if everything's 1, well, then you would get exactly 1. So it's going to want to shift towards the product side if you started everything at 1. And if K is exactly equal to 1, then delta G is 0. And, sorry, I forgot to put little knots on these to say standard state. So then you're already at equilibrium. This is reasonably uncommon, but there are some reactions, I'm sure, where if you're at exactly 1 molar or exactly 1 atmosphere, you are exactly at equilibrium. So having said that, let's do something numeric with this now. So we're going to use the tabulated free energies of formation to calculate the equilibrium constant. Note, this table comes directly out of your book. So one of the things you can do on your test is if I don't give you a value, you can look it up. These are all in your appendix of your text. I will do my best to... I'm planning to give you all of them as like a sheet at the back, but mostly I'm more thinking of like for homework problems. If you have a homework question that doesn't tell you there, you can look that up. So to use this equation to find K, that's our variable, we need to know the T, which it tells us, R is a constant. We need to find delta G naught. So we're going to go back and we're going to use the fact that delta G naught is equal to products, that's supposed to be a D, not a B, minus reactants. Therefore, my products are, I have 2 NO2s. So I have 2 times 51.3 kilojoules per mole. And then I'm going to subtract all the reactants. In this case, there's only 1. So we have 1 of our reactants, and it's got an energy of 95.7 kilojoules per mole. So I wrote both this down. Let me go look and make sure those are right. So we have NO2, which occurs here, 51.3, and we have 1 N2O4. Did I grab the wrong one? Let's see, N2O4, gas. I did grab the wrong one. This is why I look things up, because it helps us fix things. So this is 99.8 kilojoules per mole. I almost made a boo-boo. So now we have to combine these. We have 2 times 51.3 minus 99.8, now that we have the correct phases. So we have delta G equals 2.8 kilojoules per mole. So now that's a positive, and we can plug it into our equation. So we have 2.8 kilojoules per mole equals 8.314, negative 8.314, times 10 to the negative 3 kilojoules per mole Kelvin, and I didn't give myself enough space, of course, times the temperature of 298 Kelvin, times ln K. So now let's multiply all this stuff out. So we get 2.8, and I'm going to go ahead, I'll keep the units for now, kilojoules per mole equals, so we have negative 8.314 to the negative 3 times 298. So from that, I'm going to get negative 2.478 ln K. And this is in kilojoules per mole Kelvin. So I'm going to divide both sides by negative 2.478. I get 2.8 divided by that. And I'm going to get negative 1.13 Kelvin. Oh, wait, the Kelvin canceled because I multiplied by temperature. Just kidding. There's no unit. All the units canceled. Negative 1.13 equals ln K. As a reminder, to get rid of your logarithm, you raise e to the power of both of these things. So we have e to the negative 1.13, and I'm going to get that K equals 0.323. There's our value for K. So that will give us that. So K equals 0.323. So that finishes up, let me make sure. Yep, that finishes up everything we have to cover inside of the chapter on thermodynamics. So this is definitely one where I think practicing with these helps a lot. I do find that these problems tend to be easier than the ones we did in the titration section. You'll notice that they're just not as long, if nothing else. You also don't have ice tables, which helps. So these problems tend to be a bit easier, but they're a little different than what we've been doing lately. So it just takes enough practice to be able to recognize what equations you needed to use and how to manipulate those equations, especially with the Hess's law stuff. So I think practice helps a lot in this section, not that it's not always useful, but I find that especially here I see a lot more students improve significantly that at first have tremendous trouble with the Hess's law and calculating delta G's, and it just gets really a lot better after they do some practice with it. So with that, I hope you're doing all right, and I will record some more for you Tuesday.